All right, welcome back. So in the past we had talked about integrating functions, let's say f of xy, over a region in the xy plane, right? So maybe over a region that's like a solid disk or a solid triangle or some other funny looking region. Well, we can ask sort of something different too, right? Why do we restrict ourselves to kind of two-dimensional things in the xy plane? So let's say let's draw the xy plane here. And let's say I had a curve that looks something like this, right? Just some curve C, right? And I'm going to say C has parameterization given by r of t, where t is between a and b, right? So I have some curve there, and then I also want to have a function on the xy plane. So f of xy, a function on the xy plane whose domain includes C. In other words, f of xy is defined at every point along C here, right? Then what I want to ask is, can I integrate this function just over this curve instead of, over some two-dimensional thing, right? Well, the answer is yes. And so you can ask, well, how do we do such a thing? Well, just as when we're defining any kind of integral, we really need to get down and do a Riemann sum, right? So how do we do that? So the first thing we have to do is subdivide the curve into really small pieces. And since r of t kind of, tells us points along the curve here, let's say down here we have r of a, and up here we have r of b, right? The function r tells us how to move along this curve. So to subdivide the curve, we can just subdivide the domain of r, right? So what do I mean by that? I mean do something like this. So we'll call t naught a, and that'll be less than t1, and that'll be less than t2, and so on. And then tn minus 1, tn, which will be b. Right? So what we've done is we've broken the interval here into n small little pieces. Right? Okay, so what does that do to the curve? Well, let's say we define r of ti to be equal to the point pi. Right? This will just save us some writing over here. So then this first point is p naught, this last point is pn, and then at the various t values, it just cuts up the curve. So you might have p1, p2, p3, so on. And pn minus 1, and then pn at the end. Okay, so it cuts up the curve. Right? And then what I want to do is, so in each subinterval, choose ti star, right? And what are the subintervals? So the subintervals are the sort of ti minus 1 to ti, right? So for example, t1 star is between t0 and t1. t2 star is between t1 and t2, and so on. So we'll have t1 star through tn star, right? And then we know how to find arc length of a curve like this. So what we can say is find the arc length of each of these segments. So let delta S sub I be the arc length of the segment of C from Pi minus 1 to Pi. Okay? All right. So, well, here's what we're going to do now. Now we have to sample the function on each of these intervals, and that's what we're going to do with these sample points. Right? So, the sample points are, they're the image of these under the curve. So R of Ti star, which we'll call Xi star, let's use this here, Xi star, Yi star, right? And then these are the points we're going to plug into the function. So then the line integral is, well, we write integral f of xy ds. So that little s there, this d little s, that's the arc length sort of infinitesimal there. Right? So this is approximately given by the sum from I equals 1 to n of f xi star yi star delta si, right? So of course, then the actual integral is just the limit. Right? So limit is n goes to infinity of, oops, let's write the right things here, of the sum from I equals 1 to n, f of xi star, oops, f of xi star yi star delta si. Right? So you can kind of ask, what is this integral giving? Well, geometrically, let's see if I can draw this picture. All right, so what we basically have here, so here's the xy plane, and let's say we have our curve down here, and it just kind of does its thing there, right? And then we have some function that sits above it that maybe does, you know, whatever it's going to do over that curve. And then what we're really doing is finding the area of kind of the wall that's made by, you imagine you have the base of the wall. If you trace out on the floor the base of a wall, you get some curve. So imagine here we have some kind of wobbly wall, right? It's kind of like wavy shaped or something like that. So you trace that out, and then the function f, which is this pink guy up here, right? The curve is this thing down here, right? This function f should be thought of as the height of a wall, right? So you can kind of say this is going to give you the area, the surface area of that wall, right? So it could be a wall that has some wobbly base and then kind of waves on the top or something. Maybe it just keeps going up. But that's what this is giving. Right? It's giving you the area of some sheet that's kind of just wobbling around in XYZ space. All right? So hopefully that makes sense. And in the next video, we'll show you how to actually effectively compute these things.